I suppose most of you are familiar with circles. Ever since elementary school, you may have encountered them in mathematics. And what I'm gonna be presenting you today is a fundamental property about how certain angles which appear naturally within circles are connected one with each other. Namely, the inscribed angle theorem. Start by considering an ordinary circle O, and let us take 3 points on the circumference of this circle. Let's call them A, B, and C. Now unite A and B with the center of the circle O and also with the point C. As you may know, the angle C is an inscribed angle within this circle. And also the angle formed by A, O, and B is called the center angle for this circle. And of course, a question which may naturally arise is, what is the connection between them, as you can see that they are somehow related, as both of them have something to do with points A and B. It turns out that the value of the angle determined in the center of the circle is always twice the value of the inscribed angle, no matter how you position the 3 points on the circle. This can be seen really well from the animation on the screen. In the upcoming, I will be presenting you the proof of this fundamental result in geometry. When dealing with complicated proofs like this, it is important to maybe split the proof into some particular cases and then work your way on. And in fact, there are 3 distinct cases we need to work on for this problem. The easiest case to consider is when 2 points are situated on the opposite sides relatively to the center, meaning that they are situated on a diameter. The first particular case is very easy to solve and will be used in proving cases 2 and 3. The second case deals with situations where the 3 points are situated not in the same hemisphere of the circle. And finally, we will deal with the case when all the 3 points are situated in the same hemisphere of the circle. Alright, starting off with the first case, we can notice that both of these segments have length r being radii for a circle. Therefore, the triangle that they form is isosceles, and therefore this angle will be equal to x as well. We can denote the other angle of this triangle with z, and notice that x plus z plus another x is equal to 180 degrees, because the sum of the angles in a triangle is always equal to 180. On the other hand, if you look closely, y plus z is also equal to 180 degrees. So both of these quantities are equal to 180, so they have to be equal with each other. We obtain that z plus 2x has to be equal to z plus y. And by subtracting z from both sides, we get that 2x is equal to y, which was the desired result. The last step for completing case 1 is subscribing to the channel in case you haven't done that already. This concludes the proof for case 1. Moving on to case 2, let us unite all the 3 points on the circumference of this circle with its center, and notice that the segments formed now have length r. Let us also split the angle x into x1 and x2 and denote these angles by z1 and z2. Now notice that z1, z2 and y are angles formed around the center of the circle, meaning that their sum is equal to 360 degrees. Now notice that z1 is equal to 180 degrees, meaning the sum of the angles in a triangle, minus 2x1. Once again, the triangle corresponding to z1 is isosceles, therefore the other angle is also equal to x1. And in a similar manner, we get that z2 is equal to 180 degrees minus x2 times 2. Let's plug these facts into the equation and see what we get. Notice how in the left-hand side of this equality we have 180 degrees plus 180 degrees, and they sum up to a total of 360 degrees, which is exactly what we have on the right-hand side. Therefore, we can cancel out both of these terms. And what we're left with is minus 2x1 minus 2x2 plus y equals 0. And moving the minus 2x1 and minus 2x2 in the other side with, the opposite sign, we will get that y equals 2x1 plus 2x2. And we can factor out the 2 to get that y equals 2 times x1 plus x2. But remember that x1 and x2 form the angle x, therefore the sum x1 plus x2 is equal to the angle x. And we have obtained that once again y is equal to 2x, completing case 2. And moving on to case 3, let us unite this lower point with the center of a circle and form this diameter. Let us denote the angles formed with z1 and z2, and the sum x plus z1, I want to denote it with alpha 1, and we will also denote by alpha 2 the sum z2 plus y. And by case 1, alpha 2 will be equal to 2 alpha 1, because we are in the exact situation that we've been there. And let us get back to the previous notation, and we get that z2 plus y is equal to 2 times z1 plus x. And now also notice that in a similar manner, by case 1, z2 is twice the angle z1. And therefore we can replace z2 with 2 times z1. Next, we can notice that terms 2 times z1 can be subtracted from both sides, resulting in, once again, y equals to x. And this concludes the proof for case 3. Now, in case you're still watching, please consider subscribing to the channel. And thus we have proved the inscribed angle theorem. Let me know what you want me to cover next, and please leave a comment and a like if you enjoyed this video. See you on the next one.